Okay, apparently we ran into a little snag again. Let's keep going though. Forge ahead in spite of difficulties. Right, so we did the 2-point sources in phase. Let's now do the 2-point sources separated by half wavelength that are out of phase. One at angle 0, one at angle of minus pi. So, right, our psi is going to have the form pi cosine theta minus pi, right? And so the center of the circle is at minus pi this time. So I come over here, come down, and here's the center of my circle. The radius is pi, so I come back over here and strike this circle, right? Remember, theta is measured up this way. So when theta is 0, I go straight up. That's a main beam max. So as I go from theta equals 0 to theta equals pi over 2, right, I'm going to go from here down to a null. And so I go from a max to a null. Similarly, when I go from theta equals pi over 2 to pi, I'm going to go from a null to another max. So here we are. Right? So, right, when they're in phase, the main beam max is broadside to the array, right, in the theta equals pi over 2 direction. When they're out of phase, the main beam max is in the direction of theta equals 0 and theta equals pi, and theta equals pi over 2, broadside to the array, there's a null, right? So this is called in fire, right? Because it's firing down the line of the array, right? The line of the array is along here. This is called broadside, right? Because it's the main beam max is broadside to the array, right? So keep in mind now, if I take this and I spin this about the z-axis to get the three-dimensional pattern, right? If I cut it this way, right, perpendicular to the plane of the page, it's going to be isotropic, right? If I cut it this way, I'm going to get this figure 8 pattern, right? Down here, right, for the case where it's in fire, the three-dimensional pattern is spun about the z-axis, right? So you spin this, and then, right, in this plane, you get a null, right? So no matter where you go in this around the array this way, you're going to get a null. And so the half power beam width, right, here is going to be, this is going to be a beam, right? This half power beam width in the orthogonal plane here is much broader than it is here. The half power beam widths in the two orthogonal cuts for the in-fire pattern are the same. Here it's this, and then on this case it's 2 pi in the other plane. Okay, so we'll get into that later. Don't worry too much about digesting that. Okay, page 4. Trying to push ahead. Okay. Right. A little lull in the action. Back. Right. So once again, right, it's let's look at this. Right. Psi is theta d cosine theta plus alpha. For n equals 2, f of psi is sine n psi over 2 divided by n sine psi over 2, right? For n equals 2, that's going to be sine of, put 2 here, that cancels, theta d cosine theta plus alpha, right? And down here it's going to be 2 for n sine beta d over 2 cosine theta plus alpha over 2, right? So the point I'm making is, right, I can plot this function for any d, right, and any alpha. For any d and any alpha, it's a simple matter to plot this, right? So that's what this is, right? This is taken from an antennas text, right? Our antennas text that we use in the advanced class. Let's try to zoom in a little bit here, right? And so on this axis, right, the rows, uh, each new row corresponds to a different spacing between elements. Each column corresponds to a different phase shift, right? So we could use that graphical technique that we had previously. We'll do so in a moment, and we could reproduce all of these plots. Right? But in this case, these are just a quick computer simulation. So somebody just wrote a MATLAB code and made these plotted these up, right? So let's see how that goes. See, as the spacing increases, one thing you notice, zoom back out a little, be a little more conscious of what I'm showing you. As the spacing increases, right, you get more lobes in general. That makes sense from the sketching method, right? Because as you increase the radius, the circle gets bigger and bigger, and so you're going to allow more lobes into visible space. So that's a reasonable observation, right? And right. So the other thing you can observe is as you change the phasing, right, the pattern changes as well, right? So take this for example. Let's look at the 3/4 wavelength spacing between elements, and then see what happens to the pattern as you change phase from all elements in phase to all elements out of phase, right? So as it increases from 0 to 45 to 90, you can kind of see this main beam beginning to scan, right? It's moving that way. Well, that makes sense too, because the center of the circle is moving off to the right, and so the main beam max is going to move to the left rather than being at broadside, like in the alpha equals 0 case. It's going to occur for values of theta beyond theta equals pi over 2. So it's kind of scanning to the left here, right? And then 135, and then 180 degrees, then it's finally in fire, right? So it starts off broadside. Of course, you got these beams here, and then it ends up being essentially in fire. There's a little dimple in this, so the main beam max is not exactly in the direction theta equals 0 or theta equals pi, but it's relatively close to the max. Okay, so it's kind of interesting to look at these different values and that occur by virtue of the fact that the spacing between elements changes as well as the phase shift between elements change. Okay, so then, right, page 5 here, let's see what we're doing here, right? So let's see if we can predict what cases. Uh, let's see, let's pick up the d equal lambda, right? Alpha equal 90-degree case. Still n equals 2. So d is lambda, alpha is uh, 90 degrees. So that should put us here. So that's the pattern we should get. Right? Should look something like that. Should end up looking like this. Dimple, max, null, peak, null, backload, etc. That line of the array is this way. So let's check our sketching method. Right? So for n equals 2, this is the universal pattern f of psi versus psi. Right? And I can extend this as much as I want to, right? If I increase the spacing between my elements, right, theta times d is going to go up, and so the radius of the circle is going to increase. So I may need to add in more. This thing is periodic, so I may need to add in more cycles if my radius gets larger, right? But it's large enough for this purpose. Okay, so right now my center is going to be at 90 degrees, right? So that's pi over 2. So I come down here, pi over 2. Then the radius of my circle is right? 2 pi over lambda times lambda is 2 pi. And so that comes out to here, right? From here to here is 2 pi. So then I strike my circle and I'm good, right? So now remember, theta is measured up this direction. So in the theta equals 0 direction, I go up. I'm right here. I'm not at a max, right? So that's why that little dimple is in there. Then as I increase in theta, right, I'm going to ride up pretty quickly. I'm going to hit a max. So that shows this, right? I ride up to a max. Then I'm going to go down to a null. Where is that null? It's easy to find. You go straight down here and then down to the origin. The pattern from this max has to go to a null by the time theta gets from this value up to this value. And then between here and here, I'm going to go from a null to a max, null to a max to a null, right? So that's what gives me this lobe in here, right? So that's a main beam max direction. Similarly, I go from, right, a null here back up this way. So from this angle to this angle, right, here, right, I go over, and I'm not quite at the main beam max. So I don't go all the way out to the periphery of the circle. So I demonstrate that that's smaller by making that lobe a little smaller than this lobe, which is the main beam max. So, but the nulls are easy to find, right? Null come in here, null come in here. So between these two nulls, right, I have a main beam, right? Between this null and here, I go from a null to something not quite one, not quite max. So I go from a null up to not quite max. I stop here. I don't go all the way out here. Okay. And then again, right, the three-dimensional pattern is just spun about the axis. So then I can take this one, right, and I compare it to the same, right, from the numerical, and I'm pretty good. Say a decent sketch. This one should look like that one. So our sketch should look like this sketch. All right. So struggling a little bit here today for some reason. It's Monday. Maybe that's the reason. 1, 2, 3, 4, 5. Uh, let's do one more example, right? Using the sketching method. Right? Let's try this, right? N equals 4 this time. Okay, so we're going to get away from the n equal 2 case. We sort of beat it to death. And then halfway spacing, okay, phase shift of pi over 2, right? So the reference element is 4 of them. Let's pay attention to what you got here. 1, 2, 3, 4, right? They're all one, uniform illumination. Every one of them is half wavelength spacing, right? This one is one at an angle of 0. This is one at an angle of pi over 2. This is one at an angle of pi. This is one at an angle of 3 pi over 2. And you're plotting the pattern versus theta for this array of isotropic point sources. That's the task at hand. How do you do it? First, you got to plot f of psi versus psi for the n equal 4 case, right? So this has to be given, or you have to go use MATLAB to produce it. Typically, I'll give it to you. Okay, so right here's our circle function, polar circle function, right? So psi is beta d cosine theta plus alpha, 2 pi over lambda, lambda over 2, which is pi, cosine theta plus pi over 2. Center of the circle, radius of the circle. So so here's f of psi versus psi. I come to theta equal pi over 2 right down here. right? I extend my radius out to pi and I swing my circle. Then, right, then I'm ready to go. I can easily find my nulls. A null there and a null there, right? Come straight down, go in this way. So this is a null direction and that's a null direction. And in between, there's a little minor lobe. That's what I sketch. This is a null. Here's another null. In between the nulls is another minor lobe. I sketch this. This is a null. This is a null, right? Two nulls. Between the nulls in this direction is a main beam max, right? Voila, done. Okay. So that's how we sketch the pattern for the n equal 4 case, half wave spacing, right? Phase shift pi over 2, right? And you can see as alpha gets smaller, right? If alpha goes from pi over 2 to 0, the center of the circle is going to move this way. And so the main beam max is going to head to broadside, right? So you can see what happens as you change alpha, right? You can see what happens if the center of the circle gets larger, right? As the center of the circle gets larger, I'm going to start picking up these other lobes. Let's extend this some, right? This will go out this way. It will bump twice, come back up, right? So if my circle gets real large, I'm going to start picking up more than one major lobe. That's usually undesirable, okay? Not always. Usually it's undesirable to have more than one main lobe. Why? Because then you're spewing energy out in typically in an undesirable direction because you want most of your energy focused in this direction. Right? You got to put up with some energy going out in the side lobe. So these other lobes that can come into visible space when the radius of the circle gets larger or the spacing between elements gets larger, they're called grading lobes. Grading lobes. New word. Okay. Grading lobes. Okay, so here's a little problem. See if you can see what you can do with this one. Design a 5-element uniformly excited, equally spaced linear array for main beam maximum at broadside, right? And then the main beam maximum 45 degrees from the broadside. So let me give you a quick hint on that, right? This thing is going to be a max whenever psi is 0, right? So let's look at this. Let's set psi, we want psi to be 0 when theta is 45 degrees. So we want it, so psi, what is psi? It's beta b cosine 45 degrees plus alpha. So if this is the case, I'm going to have to get alpha to be minus beta d divided by the square root of 2, since cosine 45 is 1 over the square root of 2. Right? So that's a constraint. Right? Since I wanted my main beam max to be in the theta equal 45 degree direction, I knew that psi had to be 0 when I put in theta equals 45 degrees. And so I accomplished that by solving this equation for alpha when theta is 45. And that told me that alpha needed to be minus beta d over the square root of 2. Okay. So clearly then, right, when if you plug this in and then you put in theta equals 45, psi will indeed be 0 in the direction theta equals 45. Okay, so that's going to be a main beam max. Okay, so right, hopefully you can use that as a hint, right? In each case, spacing, element spacing and linear phasing such that the beam width is as small as possible, right? So the beam width being as small as possible means you want the radius of the circle as large as possible, but right? But no part of a grading lobe can appear in visible region, right? So you don't want to pick up, right? This thing is going to be extended now as necessary. Two bumps, another bump, two bumps, etc. This thing is going to be extended. Uh, I guess three bumps down here. Sorry, look at the wrong problem. This is the N equals 5 days. You're going to extend this, uh, but you don't want, right? You don't want to pick up any of this lobe. You want the circle radius to be as large as possible so that the main beam occupies the smallest amount of angular space as possible. Therefore, the beam width is as small as possible. Therefore, the directivity is increased as large as it can be, right? But you don't want to pick up any of this lobe, right? Because these are what we call grading lobes, right? These are grading lobes. So I'm going to give you an opportunity to think about that a little bit, and then I'll provide a solution for that before too much longer, and you can kind of compare your thinking to it. Right, so this is a kind of an introduction to arrays, right? Introduction to array concepts. Arrays are quite important. Why? Right? Because if we have more elements, the the electrical size of the antenna, including all elements, is larger. Therefore, the beam is smaller, right? Additionally, we can use phase shifting to point or change the main beam max direction, right? Which in our graphic technique essentially amounts to moving alpha this way or that way, and therefore moving the direction of this main beam in the space, the different directions. Right? Alpha 0, main beam max, 90 degrees. In this case, alpha pi over 2, the main beam max looks like it occurs at roughly, 135. All right, that's as much as I want to do on this today. Right. There'll be a little more coming as this week unfolds. I really want to try to knock out this, put this antenna chapter to rest this week. I'm going to do a little bit in arrays, and then that'll be it. Okay, so again, for this, there will actually be 3 videos because for some reason I punched something and it stopped recording, or maybe I can concatenate it. But anyway, they'll be annotated so that you'll be able to click on all of them. All right, keep up the good work. Hope everybody's well. Take care.